Welcome to ES 310 Lesson 8. Today we're going to be reviewing the material from Lessons 6 and 7 by looking at three new examples, one in the rectangular coordinate system, one in the normal tangential coordinate system, and one in the cylindrical coordinate system. To see the content for this lesson, check out Hebler's Dynamics Test Chapter 13 or review Lessons 6 and 7. As a quick review, these are the equations we've been working with over the last two lessons. In the rectangular system, we're using the XYZ coordinates that we're most familiar with. We sum forces in the X, Y, and Z directions, and those forces are equal to the mass times the acceleration in the appropriate direction. The accelerations are just the second derivatives of the positions for each of those directions. We use rectangular coordinates primarily when we have straight line motion or projectile motion, where we understand the accelerations or the velocities or the positions as moving along one of these coordinate directions. When we're moving along a curve, we usually use either the tangential normal coordinate systems or the polar coordinate systems, or cylindrical coordinate systems by another name. In the tangential normal coordinate systems, we have some information about the path, either the radius of that path or the expression for that path in terms of x and y coordinates. In that case, we've got the tangential coordinate that moves along, tangent to the path, and we have the normal coordinate that moves towards the center of curvature of the path. We can sum forces in each of those directions and set that equal to the mass times the acceleration in that direction. The tangential acceleration is the first time derivative of velocity, and the normal acceleration, or the centripetal acceleration, is the velocity squared divided by rho, where rho is the radius of curvature. In the polar or cylindrical coordinate system, we are typically dealing with information about rotation in terms of a change in angle. In that case, we've got the radial direction, which points out from the center through the point of interest, and we've got the theta direction, which is in the direction of that change in rotation. We can sum our forces in those two directions, and set those equal to mass times the acceleration in those directions, and our acceleration in those directions are given by these expressions. We also have a z direction in this notation, where the acceleration in the z direction is the second time derivative of the position in the z direction, which is exactly like what we had in the rectangular coordinate system. So now let's take an example using rectangular coordinates. We have a conveyor belt that's moving at a given speed, 4 meters per second, and we're given a coefficient of static friction, so this is a friction type problem, between the conveyor and a 10 kilogram package. The question is, what if we're going to stop the conveyor belt but we don't want the package to slide? What is the shortest time that the belt can stop in? Alright, so as the belt stops, we're creating an acceleration. That acceleration is creating a force on the block or on the package, B, and we want that force to be less than the force of friction so it doesn't slide. So we're given an initial velocity, which is 4. Our final velocity is going to be stopped, so that's going to be 0. And we've got the time, which is what we're trying to find. So if we start at 4 and we end at 0, we have some sort of acceleration, which we're going to have to find from the limitations placed by the force. So let's draw a free body diagram of this box. There's our box. We've got a normal force going up. We've got a weight going down. The weight is mg, normal force. We've got a friction, which is going to go this way, right? Because if it were to slide, it would slide in the direction opposite that it's moving. And our velocity is in this direction, our acceleration is in that direction. So if we sum our forces in the x direction, we have friction is equal to mass times acceleration in the x direction. And that's the acceleration we're interested in over here. We know it doesn't move in the y direction. So our sum of forces in the y direction is going to give us that the normal force up, we'll say up, and we'll say to the left. Okay, so normal force is up, and mg is down, and it's not accelerating in the y direction, right, because it's sitting on the floor or on the belt. So N is equal to mg. And F is equal to mu N equals max. So if N is equal to mg, we get that, well, we can plug this in. Mu is given, that's 0.2. Mass is given, which is 10. G is 9.81 because we're using SI system. The mass is 10, and the acceleration in the x direction is what we're trying to find. So we can find acceleration in the x direction of 1.962, which is negative, right? Because positive is to the left. We drew our acceleration to the right. That would make F negative as well. All right. So now our acceleration over here on the kinematic side is 1.962. We can write v is equal to v naught plus at, because this is a constant, right? And plugging things in, we get 4 minus 1.962. Our final velocity is 0. Solve for t. T is going to be 2.04 seconds. And that then is our answer. So we used our force equations over here, we used our kinematic equations, and ended up solving for our time. Example 2 is going to use the NT coordinates, or the normal tangential coordinates, because we're given information about this hill that our motorbike is moving on. Alright, so when we're given information about the curve, we're usually going to use the NT coordinates. So we have a motorbike. It's 800 kilograms is its mass. It's moving with a constant speed. So constant speed means speed is 80 and speed dot is 0. We're supposed to determine the normal force the surface exerts on its wheels when it reaches point A. Alright, so point A is still on a slope. Right, it's not a big slope, but it's still on a slope. So let's draw, I'm going to exaggerate that slope a little bit. Here is my motorbike. Okay. Alright, that's a little bit too much. Let me try that again. Alright, so if that is my motorbike, I've got a normal force, I've got a weight, and since the wheels are rolling, we're not worried about friction. It's not sliding. Alright, the slope here, if we extend this line, right, has some slope theta. We're going to need that theta because that theta is also relating us. This theta is the same theta up there between the weight and the normal force. Alright, so the weight is mg. Normal force we don't know, and so we're going to have to find theta at some point. We're also going to have to find, if we're using NT coordinates, if we go back up to our equations, we're going to be using these center equations, right? So AT, this is AT, so there's no tangential acceleration. AN is v squared over rho. We don't know rho, we don't know the radius of curvature at A, but we do know that we know the relationship between y and x, so we're going to use the expression rho is equal to, let's see, 1 plus dy dx squared to the 2/3, no, to the 3/2. Divided by the magnitude of the second derivative, d squared y dx squared. Alright, so that'll give us rho. how do we find theta? Theta is the slope of this curve. Well, to find the slope of the curve, we're going to take the derivative of the curve. So let's start then with that expression. We've got, start over here, y squared is equal to 2x. That means that y is equal to the square root of 2x. Right, take the derivative of y with respect to x. Square root of 2 is just a constant, and this x under the square root, we can rewrite this as the square root of 2 times x to the 1/2. Right, the square root is 1/2. So then we have 1/2 x to the negative 1/2, and we do it again, and we get the square root of 2 times 1/2 times negative 1/2 times x to the negative 3/2. Alright, at x equal to 100, then dy dx is equal to 0.0707. At x equal to 100, dy d squared y, the second derivative, is equal to negative 0.000354. Alright, this is our slope right here. The dy dx equals slope. Change in y, if we're looking at this angle, right, so change in y is going to be over here, change in x is going to be over there, so this is the tangent of theta. Okay, so from that, then we can get theta is equal to 4 degrees. So not very sloped, but still sloped, 4 degrees. Alright, let's go back to our free body diagram. If our coordinate system, we've got the tangential direction, which is along this direction, and we've got the normal direction, which points this direction, inwards. Alright, so n is along the normal direction. mg is not along either of the two directions. This is tangential, this is normal. So if we're going to sum forces in the normal direction, because the tangential is just going to be 0, nothing's happening in the tangential direction, Fn is going to equal n would be negative, plus mg. If that's theta and that's theta, then it would be mg cosine of theta is going to equal mass times the normal acceleration, which we said was v squared over rho. V squared over rho. We need to find rho, right? So we found all the parts to rho. We can plug them all in. Get rho is equal to 1 plus 0.707 squared to the 3/2 divided by this really small number, 0.000345354 squared is equal to 2,849 meters. We also, this is in, the 80 is in kilometers per hour. We need to convert that, which we can do. We need that in meters per second, because that's what the G is in, right? Alright, so we should have all the parts we need now. So we're going to have that N is what we're trying to find. Determine the normal force the surface exerts on the wheels. Alright, so N is equal to mv squared over rho minus, sorry, let's change some signs, mg cosine of theta. Plug all those numbers in. Our mass is 800. Velocity is 22.2 squared divided by rho, which is 2,849, negative plus 800 times 9.81 cosine of 4 degrees gives us something like 7,967 newtons is our final answer. So once again we have, well, we didn't use kinematics so much in this one. We've got the force equations here. We had to do some differentiation to deal with the fact that we didn't have a radius of curvature. We had the expression for the curve, so we did some derivatives to do that. We found the slope from those derivatives, and then we found the radius of curvature. And we plugged things in. Our third example is the cylindrical coordinates example. So in this case, we're given information about theta and theta dot. And that's how we know we need to use cylindrical coordinates, because we use cylindrical coordinates when we're given information about a change in angular velocity or acceleration. So in cylindrical coordinates, our expressions are all in terms of r dot, or r double dot, theta, theta dot, or theta double dot. So let's start writing out what we know about r and what we know about theta. So r is given. We have an expression for r. R is equal to 0.8 sine of theta. We also have an expression. We know that the theta we're interested in is 60. And we have theta dot of 5. And that's a constant, so theta double dot is equal to 0. Alright, so if r is 0.8 sine theta, at theta equal to 60, right, r is going to equal 0.6928. So that's just plugged in 60 into this expression. Alright, r dot is the derivative then. So 0.8 is a constant, the derivative of the sine is the cosine of theta, and then the inner derivative, because theta is dependent on t as well, we get a theta dot. If we plug in theta equal to 60 and theta dot equal to 5 into this, we get 2. Alright, last derivative, double dot, 0.8 stays out front. The first derivative, right, so the derivative of the first times the second plus the derivative of the second times the first is the way the product rule works. So the derivative of the cosine is the negative sine of theta, but theta is dependent on t, so we need a theta dot. And there was already a theta dot, so that's going to become squared. Plus the first times the derivative of the second is theta double dot. So that's 0. You plug in all the other parts. This is going to equal negative 17.32 at this specific situation, the 60 with the angular speed of 5. Alright, so let's take a look now at this little ball up here, right? And we're going to look at the free body diagram for this ball. So we've got tension acting down the rope. There's our tension. So the tension actually connects from the surface of this circle to a point at the far surface, the origin. The normal will point, it's the normal on the ball, so it's going to be pointing up, but it's along this line, right? The one that connects the center of the circle to its edge, the radius. So that's going to point that way. That's going to be our normal. And then we've got Fn, which is what we're trying to find. Fn is going to be perpendicular to the tension, because it's perpendicular to this. Let's make it look perpendicular to the tension. It's perpendicular to this shaft with the hole in it, which goes along the rope where the tension is. So that then is Fn. Whoops. Alright. And we also would have weight acting on this, except it tells us that we are in a horizontal circular path, which means gravity is acting into the slide, so we don't have to worry about weight. Alright, our coordinate system goes from the origin, right? So our coordinate system is going to point out from the origin and is going to point in the direction of theta dot. So they need to be perpendicular, but in that direction. That's perpendicular. So this is our our r direction. This is our theta direction. And we can now write our equations of motion. So Fr is going to be negative t, right, plus the component of n that is along that direction. So let's take this angle here between t and n, and we're going to call that alpha. Just, we need an angle. We'll figure out what alpha is in a second. So n, that's the adjacent cosine of alpha. And that's going to equal mass times the acceleration in r. The sum of forces in the theta direction, we've got Fn, all of which is in the theta direction. And we've got part of n, and in this case it's going to be negative that. So negative n sine of alpha, because that's the opposite part. And that's going to equal mass times a alpha, or a theta rather. Alright, so two things we have to do. We need to find AR and A theta, and we need to find alpha. And we need to talk about tension. So let's start with AR and A theta. We found all our R dots, all of that stuff. So AR, the expression for AR is equal to R double dot minus R theta dot squared. Well, we know R double dot, so that's equal to negative 17.32 minus R, which is the 0.6928, times theta dot 5 squared. So that gives us negative 34.64. Alright, then A theta is equal to R theta double dot plus 2r dot theta dot. Well, theta double dot is 0, so that term goes away. And we get 2 times 2 times 5 equals 20. Alright, so we have the AR and the A theta. Now let's talk a second about alpha. If we look at the diagram here, I'm going to change my pen color so we can see it better. Let's make it red. Looking at the diagram, we have this from the center here. We go, if we extend this down here, right, that's part of our triangle. How is that then related to theta? Okay, well, if we also go from the center down to here, right, now we have an isosceles triangle, because this is the radius, the top line is the radius, and the bottom line is the radius. So if this is alpha up here, so is this down here, right? So if that's alpha, we know that theta plus alpha is equal to 90 degrees. Because this is directly at the bottom, so this is vertical and that's horizontal, that's 90 degrees. So based on that, we have that theta alpha plus theta equals 90 degrees. If theta is 60, alpha must equal 30. So we've got alpha. Now let's talk about T. T is tension in an elastic cord. Alright? So it's a spring. We're given a spring constant, in fact. So T is equal to K times the stretch in the spring. Well, we're told that the string or the rope is unstretched at 0.25. Currently, it has a length of R. So T is going to be 30, which is the K, times R, minus 0.25, right? The current length minus the original length. So that's going to equal 30 times, the current length is 0.6928 minus 0.25. So now we are ready to plug things into these two equations. So let's take these two equations, take them over here. We get negative 30 times 0.6928 minus 0.25, that's t, plus n, which we don't know, times cosine of 30 is equal to mass, which is 0.08, 80 grams, right? But mass is in kilograms, times AR, which is negative 34.64. Alright, n is the only unknown there, so we get n is equal to 12.14 newtons. It's part of our answer. The other part of our answer is the other equation. So we've got Fn, what we don't know, minus 12.14 times sine of 30 is equal to mass, 0.08, times a theta, which is 20. Fn is the only unknown. Plug everything in. We get Fn is equal to 7.67 newtons, which is the other part of our answer.